In this video, I'll talk about analyzing circuits that contain operational amplifiers. This relies on our usual analysis techniques: KVL, KCL, Ohm's law, nodal analysis, and so on, in addition to the ideal op-amp rules that I presented previously. First, I'll review the rules governing ideal operational amplifiers. This is the circuit symbol for a typical op-amp. There are two input terminals, one output terminal, and two power supplies. When we analyze op-amp circuits in this course, we'll make three assumptions about their behavior. First, the currents into the input terminals are zero. Second, the voltage difference between the input terminals is zero. And finally, the output voltage is constrained to be within the range of the external voltage supplies. In our analyses, if the external voltage supplies are not specified, we'll assume that they're such that they don't restrict the output voltage. That means that we won't actually use this third criteria for the most part. However, if we're actually constructing and testing an op-amp circuit, we have to make sure that these supplies are set appropriately for the desired output voltage. The assumptions or rules from the last slide lead to a few guidelines relative to analyzing op-amp circuits. The output current of the operational amplifier is the current delivered by a dependent voltage source, and it's supplied by the external power supplies. It's an unknown and has to be treated as such. Since the output current is unknown, applying KCL at the op-amp output terminal is generally not useful unless you need to find the output current. Since the current into the input terminals is zero, we do know something about the input currents. That makes it usually productive to apply KCL at the input terminals. KCL at the input terminals will generally be my starting point for an analysis of an op-amp circuit. Finally, if the supply voltages are specified, you should always check to make sure that the output voltage is inside the range specified by those voltages. This is our first example. We want to find the voltage V out at this terminal. Notice that the input voltage, V in, and the output voltage share the same reference. The supply voltages, if they were given, would need to be relative to this reference as well. First, let's take a look at what we know about the input voltages. The non-inverting input terminal is connected directly to ground, so we know that that voltage is 0 volts. That means that since the input terminals have to have the same voltage, that this node's voltage is also 0 volts. Now I'll apply KCL at this node and see where that leads. So KCL at node B, assuming that the positive currents are leaving the node and that all currents are leaving the node, this current is 0 volts minus Vn over Rn, plus this current is 0 volts minus V out divided by this resistance, Rf, and that equals 0 because the current into the inverting terminal is 0 amps. Now I can take V out to the other side. V out is equal to negative V in multiplying through by Rf gives me Rf over Rn. That tells me what V out is as a function of V in. Now let's try determining V out for this circuit. Looking at the voltages at the input terminals doesn't give me much information directly. It's not obvious to me what either of those voltages are. So I'll label the voltages at both of the nodes and do KCL at both nodes. After I do that, I can apply the op-amp rule that the input terminal voltages have to be the same. So if I do KCL at A, that means this current plus this current is equal to 0. So VA minus 6 over 20 ohms plus VA minus 0 over 10 ohms is equal to 0. Multiplying through by 20, I get 3 VA is equal to 6, or VA is equal to 2 volts. Now do KCL at B up here. So this current, which is VB minus 0, over 50 ohms, plus this current, which is VB minus V out, over 100 ohms, is equal to 0. If I do the algebra here, that tells me that V out is equal to 3 times VB. Now I can invoke my op-amp rules that VA is equal to VB. If I equate these two here, V out is 3 VB, which is 2 volts, so V out is equal to 6 volts. Analyzing op-amp circuits tends to be fairly easy, so don't make it harder than it needs to be. Next, I'll take a look at some useful op-amp circuits, do some analysis of them, and talk about particular applications for those circuits and why op-amps are so useful.